Welcome to my new section. In the last section, we will discuss about the basics of neural network. In this section, we are going to discuss about the characteristics of neural networks. The three main characteristics of neural network are activation function, network topology or architecture, and the training algorithm. The different variants of neural network each can be defined in terms of these characteristics. First one is activation function. The activation function transforms a neuron's combined input signal into a single output signal to be broadcasted further in the network. Second characteristic is a network topology or architecture. The network topology describes the number of neurons in the model as well as the number of layers and the manner in which they are connected. Third one is the training algorithm. It specifies how connection weights are set in order to inhibit or excite the neurons in proportion to the input signal. So coming to activation function in detail. So activation function is a mechanism by which the artificial neuron processes incoming information or incoming signal and passes it throughout the network. In the biological case, an activation function could be imagined as a process that involves summing the total input signal and determining whether it meets the firing threshold or not. If so, the neuron passes on the signal. That is, if the neuron will meets the firing threshold value, then the neuron will passes the signal on to the next neuron. Otherwise, it does nothing. In an artificial neural network, this is known as a threshold activation function, as it results in an output signal only once a specified input threshold has been attained. So let's consider an example for a threshold function. So consider this graph. Here in this graph, the x-axis represents the sum of the input signals of an activation function and the y-axis indicate the output signal obtained from an activation function. The value of output signal obtained from an activation function. In this case, here the zero value. So till the value 0, there is no increase in the output signal. That means the neuron will fire when the sum of the input signal is at least 0. Because its shape resembles a stair, it is clear from this diagram that the output signal will resemble the shape of a stair or a step shape. So, because its shape resembles a stair or step, it is sometimes called a unit step activation function. And its output value ranges between 0 and 1. So the f of x is the activation function. F of x is equal to 0 if x less than 0 and f of x is equal to 1 if x greater than or equal to 0. The threshold activation function is rarely used in artificial neural network. So coming to another type of activation function, that is sigmoid activation function. It is the most commonly used activation function and it can be represented by using the formula f of x is equal to 1 by 1 plus e raised to minus x, where e indicates the base of the natural logarithm, approximately 2.72. So the sigmoid activation function has a shape of step or S shape. So its output signal is not a binary value and the output values can fall anywhere in the range from 0 to 1. The sigmoid activation function is differentiable, which indicates that it is possible to calculate the derivative across the entire range of input. This feature is crucial to create efficient artificial neural network optimization algorithm. It is most commonly used activation function and it is used as a default activation function. Some neural network algorithms allow a choice of alternatives. The primary detail that differentiates the activation function is the output signal range. Typically, this is one of the range between either between 0 or 1. or between the range between the value range between -1 and +1, or minus infinity or plus infinity, etc. The choice of activation function biases the neural network such that it may fit certain types of data more appropriately. The activation different types of activation functions can be used for the construction of specialized neural networks. Now let's discuss about some other types of activation function, that is linear activation function and Gaussian activation function. The linear activation function result in a neural network very similar to a linear regression model, whereas the Gaussian activation function result in a model called a radial basis activation function, or in short it is called we call it as RBF network. Each of these activation functions has strengths better suited for certain learning tasks and not the others. This is the graphical representations of different types of activation functions. So the first, this graph represents the linear activation function. The second graph, this represented the actuated linear activation function. This indicates the hyperbolic tangent activation function. And the last one, this graph represents the Gaussian activation function. All these activation function, the range of the input signals will vary. The range of the output signal will vary, and the shape of the activation output function will also vary. Now let's see what is a squashing function. The activation functions like the sigmoid are sometimes called squashing functions because it squeezes the input signal into a smaller range of output. The solution to the squashing problem is transform all neural network inputs such that the features values fall within a small range around 0. Typically, this involves standardizing or normalizing the features. Next, let's discuss about perceptrons. Perceptron is none other than a type of artificial neuron. It is developed in 1950s and 1960s by the scientist Frank Rosenblatt. A perceptron takes several binary inputs, as I told you in the previous section, like x1, x2, etc., xn, and produces a single binary output. So, which is the perceptron? A single perceptron is indicated in this figure. That is x1, x2, x3 are the different binary inputs, and it will produce the single binary output. So the neuron's output 0 or 1 is determined by whether the weighted sum, that is sigma wj into xj, is less than or greater than some threshold value. So the output of a threshold perceptron can be indicated by output is equal to 0 if and only if sigma j wj into xj less than or equal to a threshold value, and the output value is equal to 1 if and only if the summation of wj into xj or sigma wj into xj greater than a threshold value. So this is another representation of a scheme, the same perceptron. X1, x2, etc. Xn are the input signal. W1, W2, etc. Wn are the weight assigned to each of the input, and sigma indicate the summation, and this indicate the activation function. Sigma I is equal to 1 to 0 wi xi. This is the summation function. The neuron will fire the output to the next neuron if the output of the summation reaches a threshold value or not. So this is another representation of perceptron. All these figures indicate the same concept. These are the inputs I1, I2, etc. In weights W1, W2, etc. Wn. Sum the weight into input is summed up. The input signals are summed up within the cell body, and the sum is given to the activation function. And if the value of the activation function reaches a threshold value t, then only it will fire the output to the next neuron. If the value of the output function activation, if the value of the activation function here is less than a threshold value, then the neuron will not passes its signal to the next output neuron. The neuron will passes the output signal to the next neuron only if only if it reaches the threshold value. Perceptron can represent all of the primitive Boolean functions like AND, OR, NAND, and NOR. This is all about the perceptron. Thank you.